Welcome to The Explainer. Today, we are diving into a really fascinating, honestly game-changing shift in the world of artificial intelligence. For a long time, AI has been totally obsessed with generating things pixel by pixel. But we're going to explore Meta's new architecture, a model that's attempting to step away from all that and actually move toward true, human-like, common-sense understanding. Okay, let's just dive right into this by addressing the elephant in the room, the glaring, multi-fingered mistakes that current generative models constantly make. I mean, if you've played around with AI image generators, you know exactly what I'm talking about. You get this otherwise breathtaking, hyper-realistic portrait, and it's completely ruined because the person has 6, maybe 7 totally distorted fingers. Why does an incredibly advanced machine, capable of mimicking the exact lighting of a Renaissance painting, completely fail at knowing what a basic human hand looks like? Well, it all comes down to how it views the world. Here's our roadmap for today. We'll cover current AI's pixel problem, LeCun's human-like vision, meet the I-JEPA motto, predicting concepts, not pixels, maximum efficiency, and finally, the future of AI. Starting off with Part 1, current AI's pixel problem and the inherent flaw in generative architecture. So, the crucial point here is that generative methods try to fill in every single bit of missing information by predicting exact pixel values. The way they learn is by having portions of an image removed or distorted, and then they basically scramble to guess the exact missing pixels to fill in the gap. But think about how chaotic that really is. Our real world is inherently unpredictable at a microscopic level. Like, when you look at a tree, you don't memorize the exact position of every single leaf, right? You just understand the broader concept of a tree. Generative models, however, obsess over the digital leaves. And because these generative architectures focus so heavily on those irrelevant, localized details instead of high-level concepts, they end up failing to capture the predictable reality of the world. They are trying so hard to guess the exact color of a single pixel on a knuckle that they completely forget a human hand only has 5 fingers. They produce these glaring errors that a human would never, ever draw, simply because humans possess common sense background knowledge, and well, these generative algorithms just don't.
Which brings us to Part 2, LeCun's human-like vision and a new architecture for world models.
Yann LeCun, Meta's chief AI scientist, brilliantly illustrates the end goal here. He proposed an architecture intended to overcome these exact generative limitations. He doesn't want an AI that just memorizes data or blindly hallucinates pixels. Instead, his vision is to create machines that actually build internal models of how the outside world works. By doing this, the machine can learn faster, plan complex tasks, and readily adapt to entirely unfamiliar situations, much like a biological brain does. But how do you actually teach a machine common sense? You obviously can't just type out every rule of the universe. Instead, these systems must use self-supervised learning. This means the AI learns directly from raw, unlabeled data, like just looking at images or listening to sounds, without researchers needing to manually label every single file. Think about it. Humans learn an enormous amount of background knowledge just by passively observing the world around us. And self-supervised learning aims to let AI do the exact same thing to build its own common sense. Moving on to Part 3. Let's actually meet the I-JEPA model, the Joint Embedding Predictive Architecture. Now, the core difference between the old way and this new way is absolutely fascinating. While generative models guess the exact missing pixels to reconstruct a signal, JEPA steps back. It predicts representations at a high level of abstraction. So it compares abstract concepts of images rather than comparing the raw pixels themselves. It really doesn't care about the exact shade of brown on a dog's ear. It just wants to predict the abstract concept that, hey, a dog's ear should be there. Let's dig deeper into that in Part 4, Predicting Concepts, Not Pixels, and how I-JEPA builds semantic understanding. So, under the hood, Meta uses what they call a multi-block masking strategy. First, a vision transformer, or VT, context encoder processes only the visible patches of an image. It's kind of like looking through a peephole. Then, a narrow predictor network takes that limited context, looks at a targeted, unseen location, and outputs a semantic idea of what should be there. The AI uses a single context block to predict various target blocks originating from that same image. It's essentially acting as a primitive world model, mapping out spatial uncertainty. And when researchers wanted to see what the AI was actually imagining, they trained a decoder to sketch out I-JEPA's abstract predictions back into actual pixels. The results were pretty incredible. When prompted, the model correctly captured positional uncertainty and produced high-level object parts. It knew exactly where the top of a dog's head should be, the correct angle of a bird's leg, and the proper pose of a wolf's front legs. It clearly recognizes the semantics, the underlying meaning, of what it's filling in, completely without relying on memorized pixel patterns. That brings us to part 5, maximum efficiency, and how this achieves state-of-the-art results with less compute. 632 million. That's the number of parameters in the visual transformer model meta-trained using this architecture. But here's the truly mind-blowing part. They trained this massive model using only 16 A100 GPUs in under 72 hours. In the world of AI training, which usually requires massive data centers churning away for weeks or even months, pre-training an architecture this robust in under 3 days on just 16 GPUs, that is astonishingly efficient. And that efficiency doesn't stop at the hardware, it extends to the data itself. Amazingly, this model achieved state-of-the-art performance for low shot classification on ImageNet using only approximately 12 labeled examples per class. Because it learns strong, off-the-shelf semantic representations directly from the environment, it barely needs any human handholding to figure out new categories. The competitive advantage here is undeniable when you look at the balance of performance versus pre-training GPU hours. Compared to I-JEPA, other common methods like invariance-based pre-training or traditional generative methods require anywhere from 2 to 10 times more GPU hours. And despite burning all that extra computing power, they still end up with worse error rates on the same amount of data. I-JEPA is just highly accurate and incredibly lean. Finally, part 6, the future of AI and the move toward human-level intelligence. Look, I-JEPA is a monumental achievement, for sure, but it's just the very first step toward applying self-supervised methods to a general model of the world. The really exciting future lies in extending this architecture beyond just static, silent images. Researchers are actively looking forward to integrating richer modalities. Imagine AI combining image-text paired data or analyzing continuous video data. The ultimate goal is to enable an AI to watch a short video clip and accurately make long-range spatial and temporal predictions about what will happen next, potentially even conditioned by audio or text prompts. As we wrap up this explainer, I want to leave you with a provocative thought. We're moving from machines that blindly copy pixels to machines that actually understand the physical rules of our environment. Once machines master the common sense background knowledge of our world, the kind of stuff you and I take for granted every single day, there is absolutely no telling what complex, real-world problems they'll be able to solve. Thank you so much for joining me, and keep questioning the future.